Hello and welcome. Today is Friday, April 17th, and today is finals review number 6. We are almost done with the review series. Just one more to go on Monday. Today we will talk about momentum and collisions. Actually, we should finish off yesterday. Yesterday we covered all of energy, but skipped out on power. We'll finish off power, talk about momentum. We got a tippers and another explanation type FRQ to do at the end. All right, let us begin with power, and of course this is mechanical power, and we can say that mechanical power is work per time or some sort of energy per time. So 1 watt, which is the unit, is equal to 1 joule per second. 1 joule per second. And there are other ways to find power depending on what kind of system you have. If you are, let's say you're pushing a box forward with a constant velocity v, so you apply a force Fa, and of course there's some sort of friction the other way that is slowing you down, and by applying this force you maintain a nice constant speed. Okay, so you're applying a force, you are doing work as a function of time. If you recall that work is equal to force and distance, and so you get d over t giving you force times velocity. So the applied force that you are applying times the velocity of the object, this constant velocity, would give you how much power you are providing to the system. Of course, it's not accelerating. Friction is doing negative work. There must have been some sort of jerk at the start to get it going. We started, if we started from zero velocity, we would have to accelerate to v first. Of course, that part is ignored. But once we've achieved v and we go at constant speed v, that means the applied force is equal to the frictional force, or whatever drag forces you may have. And the power output, you have to continuously burn energy every second to maintain this velocity. Otherwise, if you don't provide this power, then the friction would slow it down, decay the kinetic energy, convert it into heat, and then eventually the box would come to rest. Right. Okay, so that's power. Power is a scalar quantity. Power is scalar. So you can just add them, no need to worry about vector quantities. In circuits, you saw that whether it's series or parallel did not matter. The power can just be added together. Even in combination circuits, so if one of them is series with a parallel of another branch, then all of the powers can be added up scalarly. Okay. Let's talk about momentum today, which is very important. Right? If there is a topic that the College Board would like to choose, it's either rotational dynamics or momentum with a little bit of energy involved and energy incorporated with it. Momentum, lowercase p, is a vector. It's equal to mass times velocity. What is momentum? Well, it's this innate ability to continue to move forward. It's kind of like a a quantifiable amount of inertia in that. It shows you how much of a physical quantity you have in a certain direction, and it takes a certain amount of force to change the direction of that momentum, either to slow it down or to deflect it in some way. There are no new units. It's just the combination of the old units. So the units for mass would be kilograms. The units for velocity is meters per second. So we get kg meters per second. Okay. All right. Vector addition still applies here, so you can add momentum vectors, just like you did with 2D vectors for dynamics. What else? Let's see. Force is defined as the change in momentum per time, dp dt. And so the change in momentum must equal force times t. Fat equals delta p. This is the impulse momentum theorem. Okay. Where delta p is impulse, which is also the change in momentum. I'll just say mo, change in mo. And depending on what college you take physics in, some older textbook or some other variations of textbooks will use capital J, the variable, not the unit. The unit, of course, is joules. Capital J for impulse instead, but we will stick to delta P. Impulse is also a vector technically. That's because F is a vector, T is some sort of scalar quantity, so it doesn't matter. And so it must be some sort of vector. There is a direction. It's the way that the force is applied. So if an object is moving with some velocity v and crashes into a wall, the wall must be applying a force onto the ball. The force on ball by wall, FBW, it points in that way. Therefore, the impulse must be pointing that way as well. So if I did an FBD, we see that there's a force FB dub on the ball. Newton's third law still kicks in, right? For every action, there's a reaction. So that means there's also a force on the wall by the ball. Okay. Remember that momentum is a vector quantity. Therefore, the final momentum, P final, is going left, whereas P initial, this P is too big. It should be lowercase p. P initial is going to the right. So pay attention, be aware of the direction of the momentum. Left is inherently negative, or classically negative. So if I did the change in momentum, which is the final momentum minus the initial momentum, this would give me mass times velocity final minus mass times velocity initial. And using left and right appropriately, we can see how the final momentum is left, and you double up if it bounces back. So you would have minus and minus and your impulse or your change in momentum would be pretty big. Momentum is conserved. It's always conserved unless it's not conserved. P is conserved unless acted upon by an external force. Right? So you have to differentiate your internal forces from your external forces, and based on how you define your system, you can change the answer, basically. Right? If you expand your system out to the entire universe, then yeah, momentum is always conserved. Right? Energy is conserved, or whatever, assuming the universe is a closed system. Momentum is conserved unless acted upon by an external force. Okay, so make sure you pay attention to how the system is defined, what elements are part of the system. So another way of writing it would be P final, or it's P initial equals P final. Puff. Right. This one, recall, this one is capital P without a vector hat. This is lowercase p with a vector hat. Okay, so question, if I threw a ball, and it's a clay ball that sticks to the window here, versus using some sort of rubber ball of same mass, that when I throw it with the same velocity, it crashes and then bounces back the other way with the same velocity. Which one does more damage? Which one is more likely to break our window? More likely to break the window. Oh, should we do a poll? Let's do a poll. Cloudbot. Alright, so you should vote A for rubber, clay. Question mark. And then vote B for the rubber one. Start poll. Boom, now it started. So exclamation mark vote, and then make sure you put a little space after the word vote, and then A or B inside the box. Ooh. Oh man, we're nearing 50-50. We have 4-3 ratio. Ah. Or is it C? Yeah, it cannot be. Change my mind. Man. All right. So is that it? Anyone else? We have more people here. There's just some are lurking. We have a bunch of lurkers, not in chat. Well, close poll complete. Boom. Check that out. It's a tie between A and B. Let's see. Well, how do we figure out if we're going to break something? If you punch someone, how do you know if you're going to break their bone? Ooh, yikes, that's a morbid example. Well, if there's enough force, right? If there's enough force, then you might break the window. What force could this be? Well, it must be the force of impact. Force of impact. It would have to equal your change in momentum per change in time. Okay, and this is where it gets tricky to answer this question. This is P final. Let's just take a look at delta P, which is P final minus P initial. Which one has the greater change in momentum? Which one has the greater change in momentum? All right, so this one has P initial, which is equal to mass times velocity. This one has P final of 0. Look, velocity is 0. It sticks to the window. Whereas this one has Pi equal to mass times velocity, and PF is not 0. PF is mass times velocity, but the other way, so we'll call it negative. Ah. Yeah, so what is my delta V? Delta P. Of course, the one that bounces back has twice the amount of change in momentum. So for A, delta P is equal to mv. For B, delta P is equal to 2 mv. Yeah, it's twice the impact. Now, of course, we would have to assume this delta T, and we have to use some background knowledge to figure out how this would impact us, delta T. Okay. Even in an ideal case where the time is the same, of course you can conclude that B has more a bigger impulse, therefore the impact force itself must be bigger. But let's take a look at a more realistic approach. So when something is crashing in, especially for like things like this PIC collision with clay ball, okay, it's going to take time for the object itself to morph and change shape. Okay. And so it actually takes more time to come to a stop for the clay ball. And so your delta T is actually bigger. Not only is delta P smaller, but delta T is even bigger. Therefore, the force is definitely weaker. Whereas with a rubber ball, when it bounces, if you just hit the wall and then bounce, it happens a little faster. Now it also depends on how much bendiness you have in your ball, how elastic the ball is, right? And so how much it bends will take some fraction of a second as well. And all things, when they're bouncing, do morph or kind of bend a bit. I don't know if you guys remember the golf ball example. Let me pull it up. Slow motion golf ball. Wow, Google already knew I was going to type it in, and it typed it in for me. That just shows you how they are tracking what I am saying, I guess. Where is it? Slow motion. Oh yeah, you guys remember this video. PowerPoint, boom. This thing here. Here's a golf ball crashing into a steel plate. Look what happens to the golf ball. Wow. And so during the impact, it takes some amount of time, and then we do some frame-by-frame video analysis from the center of mass of the ball, and then we calculate. Oops, baby's crying. BRB. All right, so golf ball. Oh, that's too many videos. Yes, the rubber ball will definitely do more damage. All right. Yeah, golf balls. It looks like a little squishy rubber ball, doesn't it? Yeah. All right. Okay, let's do some conceptual stuff. Here's a nice Tipper style question. Boom. It says, oh, can I zoom in? Oh, I can't zoom in. Mode. I can't zoom in. Tipper's flashback, yeah. It says, oh, I'll just read it out, I guess. Or you can zoom in into the video. 2 blocks are released from rest at the same height. Block A slides down a steeper ramp than block B. Both ramps are frictionless. The blocks reach the same final height indicated by the lower dashed line. Right. Block B weighs more than block A. Ooh, that's kind of important. Full screen it and you can. I can. Oh, can I? Not on. Here, I guess I could do this. 1 second. There you go. So block B weighs more than block A. Is the work done by the gravitational force? So this question combines everything from yesterday and today. So, is the work done by gravitational force on block A greater than, less than, or the same as the work done by the gravitational force on B? Should we do another poll? Or we just have people? The work is the same. They lose the same amount of peg, which is converted to me. Converted to k. Converted to k. Oh, less than B because B weighs more. Ooh. Is the work done by the gravitational force? Is there friction? No, there's no friction. Look, it says both ramps are frictionless. Both ramps are frictionless. Sword Hero, go back to sleep. No, this is not honors. This is AP1. Yeah. You were snoozing yesterday. BQ. So there it is frictionless. The masses are not the same. The masses are not the same. Right? So is the work done by the gravitational force on block A greater than, equal to, or less than? So let's take a look. What is the work done by the gravity? Work done by the force of gravity must be equal to the force of gravity times d times cosine of the angle between them. Okay. Now if I do it on a ramp, here's my ramp. Let's just look at the left block. Figure not drawn to scale. Disclaimer. Here's my left block, which has some angle theta. It's much steeper. From the center of mass, let's go and draw an FBD. The force of gravity is straight down. We can call it mg. Or I'll just write both. Fg is equal to mass times gravity. Okay, but notice how displacement is actually along the ramp. This is the displacement vector. Okay. So we have to look at the components parallel to the ramp and perpendicular to Fn. Of course, there's a normal force here. It's frictionless, so there's nothing else. Okay, and which component is parallel to displacement? It is mg sine theta that is parallel to it. So mg sine theta is what's going to pull us down the ramp. Or look at it from an energy perspective. Instead of dynamics, look at it from energy. The work done by gravity will be equal to the change in the gravitational potential energy. Or sorry, I should say equal to the change in kinetic energy. Gravity is going to accelerate me. And the change in my kinetic energy will be straight from the gravitational potential energy, right? And so we look at the height differential for that. Height difference. Now delta H is of course the same, but M is not. M is not. B weighs more. B, even though it goes down a less steep ramp, the height differential is the same, but this is big M. I should say B. And so it starts off with more potential. Therefore, it has more kinetic. It's all just a wave in the Higgs field. Does it even matter anyways in the grand scheme of the those are our APC insider jokes. All right, let us go back. So masses are different. So pay attention to these little key details, like B weighs more than A. That'll kind of change everything. Now, if you consider the velocity of the object, the final velocity, of course, if you consider, no. Stop it, Sword Hero. If you consider the final velocity, the masses cancel, right? Peg magagas to Ke. Peg, if peg is equal to Ke, then mgh is equal to 1/2 mv squared. And the masses cancel. Velocity is root 2gh. Right? Since the h is the same, then they have the same final velocity because it's frictionless. But doesn't mean they have the same kinetic energy. Remember, kinetic energy is 1/2 mv squared. So because B has more mass, of course it has more kinetic energy. Alrighty then. Next up. Is the speed of block A greater than... Oh, we just did that. Oh, whoa, look at all these Gen 1 physics students coming in. The Gen 1 students. Alright. Part C says, is the momentum of block A greater than, less than, or the same as momentum of... So easy stuff, right? So we concluded that kinetic energy for B is more because mass of B is bigger than mass of A. even the velocity of course is the same. Same thing with momentum. Momentum of B would be based on the mass of B times the same velocity V, and therefore momentum of B is much greater than momentum of A. All right, so it says explain reasoning. Explain reasoning. Now you can use the equations as part of your reasoning, of course, but don't just stop there. When you're taking your AP test, make sure you are thorough in your explanation. Okay, use the equations, but also write out what you're trying to say with those equations. Okay, so in complete sentences with proper grammar, etc., so that it's understandable. Momentum of B is greater than momentum of A because mass of B is still greater than mass of A, and they still have the same velocity as was calculated earlier in part B. But also, don't just reference part B, rewrite it. So even though you're while explaining part C, you would say, as stated in part B, velocity is equal to square root of 2gh. So restate it. All right. So that was the tippers. We just have one more thing to do today, and then I actually left a couple of questions on Canvas. I'll do part A and B here on stream, and then you'll use this information to do part C and D. You can leave the answers to part C and D in the comments below on the YouTube video when I upload it. So here we go. Free response question, data analysis. All right, so another graph. I just have a feeling there's going to be a graph or something, either on the C test or the 1 test. A student drops a 6.8 kilogram bowling ball onto a trampoline and allows the bowling ball to bounce 1 time. Do you want us to answer them on Canvas, YouTube, or both? YouTube is fine. A student drops a 6.8 kilogram bowling ball onto a trampoline and allows the bowling ball to bounce 1 time. The graph shows the vertical velocity of the bowling ball as a function of time, where upward velocity is considered positive. How can this graph be used to determine the acceleration of gravity? So what kind of graph is this? This is a velocity time graph. So let me redraw it here. So we have a velocity time graph, VT. Ooh, good job, bubble guy. Potential energy tube. So it goes downwards first, and then there's a spike. What is this thing? What is this spike indicating? What is happening? Chat, what is happening? Derive it. A big force just acted on it. Yeah, so what force acted on it? What force is it? Well, what is our system? It's a bowling ball, right? It crashes into the trampoline, and then the trampoline provides a force upwards, accelerates it the other way. And so now the velocity from going, so this, now all of this, so it's not just the downwards portion, all the way up to here, my velocity is negative, right? So velocity is down below the x-axis. So all of this means that it was on its way downwards, and so if I model this out in the real world, and here's our trampoline, or the space-time fabric itself. And the trampoline kind of dimples downwards. Here's our ball. When we've reached our lowest point, that's when our velocity hits 0. When the ball is at its lowest point. Oh, this trampoline drawing does not make any sense. Let's try again. There we go. Here's our trampoline. Of course, we're warping the space-time fabric all the way out here. It's nice and stable, and so on. Okay. So the 0 represents when the ball is all the way down here. We've stretched out a spring-like material. And then we get it back. We start going, accelerating really quickly. When do I hit max velocity? Okay. The maximum velocity happens when all of my PES energy, so right now we have PES, all of that PES energy converts into the KE here. Now, if you want to get into the nitty-gritty, consider actually majoring in physics, where, yes, it's still going upwards relative to this height. You're going upwards, and somewhere, you're still gaining some gravitational potential energy relative to this height. So there is a little fight between the KE and the gravitational potential energy, but we're going to ignore that in AP Physics 1. We'll just say that all of my PES converts into KE when the trampoline gets back to its original height, and from there the kinetic energy converts into pure pegmega, the vanilla flavored pegmega, not the grape flavored pegmega we were talking about yesterday. After it equilibrates, good. And the ball will bounce up again. Is that the maximum? Well, here. So velocity is all positive all the way up to this point. So this point is when we've reached all peg. My max velocity, let's use some other colors, blue. My max velocity, blue, which is this point. My max velocity happens, as Ion pointed out, when we've equilibrated, so when we're on our way up and we're back to the original height of the trampoline. Okay, because after we leave the trampoline, we are affected by gravity, and you can see the negative slope indicates that we are accelerating downwards at the rate of gravity. All right. So finally, let's get to the actual question. The question says, how can this graph be used to determine the acceleration of the gravity? Well, I went too fast there. I kind of did it blindly. The slope, of course, the slope of velocity time, VT graph, graph, gives acceleration. All right, and we have to take the slope at particular times. So you would have to not only just say take the slope, but actually point it out, because the question asks for how can the graph be used to determine the acceleration of gravity? The slope gives you the acceleration of the ball as a function of time, and the acceleration of the ball is changing, right? Because it is being affected by different forces. At first, it's being affected by gravity only, and then it starts being affected by the trampoline, the spring force, and then back to gravity. So you would have to indicate that only for certain parts, if I use orange here, starting from here to here, we can say that the slope in this region should give you the acceleration due to gravity, because the net force on the ball is due to the gravitational force only. Okay, so be very specific when you justify or explain your reasoning. You could also, if you want, do it from here. Once we've reached maximum velocity, the slope from here to here, or whatever it is, you can also go down all the way out here. It looks like it's nice and constant slope. It should be the same as the first part in section 1 or section 2. section 1 or section 2. All right. Before we move on, let's do a side question. Y'all ready? Okay, so we have a velocity time graph. What would the momentum time graph look like? What would the momentum time graph look like? Whoa. Momentum is equal to mass times velocity. Mass is a scalar. What is a scalar? A scalar scales a vector. Whoa, hence the name, scalar. The only thing that is being changed is that the velocity values are being multiplied by some value m. Okay, the shape of the graph is the same, yeah. It's just the scale of the graph, because we multiplied it by a scalar, the scale of the graph would be different, right? So if I were to use this graph starts from 0, and then it goes down to 4 meters per second, or -4, I should say. -4 meters per second after 0.4 seconds. Right, so this is the velocity graph. I'll use black for velocity as a function of time. Okay, let's go and use pink. Pink would be momentum as a function of time. Okay, since momentum is just the scale value, the mass of the ball was given earlier in the paragraph. A student drops a 6.8 kilogram bowling ball. Okay. Yeah. You know, we got to change it up. See, every generation, every iteration, it's always slightly better, slightly different, right? It gets harder every year. The competition changes, so we have to continuously push our students to reach higher and higher bounds. So whatever we did just the first generation, you know, it's old school now. So now we have to teach them even more complex things like it's unfortunate that these kids can't do the 3D printing stuff we had planned at the end of the year because school got canceled. All right. Anyway, so if I did a pink axis, my pink axis, let's see. I did a momentum axis. The momentum, of course, measured in kilograms meters per second. Okay. When we've gone down to here, the 4 meters per second would correlate with 4 times 6.8 kilograms meters per second. What's 4 times 6.8? I don't know. Chat, help me. 4 times 6.8. Oh, too late. 27.2. So this would correlate with -27.2 kilograms meters per second worth of momentum. So the graph would look the same. It just has a different axis, a different scale factor. Yeah, 3D printer. Things have changed. All right. Let's take a look at question B now. Question B, or part B, I should say. Part B. For parts B and C, actually parts B and C part C and D I posted. We'll do B. For parts B and C, full credit will be awarded only to responses that show equations, calculations, and verbal explanations for how quantities were found from the data. As you can see, as I was saying, don't just use equations, but also explain what you want to say with them. So in sentences, in complete sentences, write down what you mean. What is the ball's change in momentum as a result of being in contact with the trampoline? So we have to figure out the change in momentum. Change in momentum, of course, is delta P, and delta P is equal to P final minus P initial. The final momentum is mass times the final velocity. The initial momentum is mass times the initial velocity. Right? So we know what the mass is. What we don't have is the final velocity and the initial velocity. So this is where we go back to the graph. Here's the graph. And so based on the fact that it was accelerating negatively downwards gets bigger and bigger, or more and more negative, at some point it stops going negative, right? And then instantly we start moving. So the lowest point is when we first contact the trampoline, and then the highest point is when we stopped again on the other end. My change in momentum happens during the collision point, so during the contact point. So from the bottom here to the top. And so based on that, we will be able to figure out what the initial velocity is, and what the if I follow the black line, there we go, what the final velocity is. Right. Okay. If I wanted impact force is just delta P over delta T. The other things that we didn't, the other stuff that we should cover is the type of collisions. There are part C and D, so take a look at Canvas for C and D and then answer them on in the comments below. Collisions, we have elastic, and by definition, both μ and Ke conserved. Then we have inelastic. Inelastic collision. Only a momentum conserved. And we also have PIC, perfectly inelastic. Only μ conserved. Most Ke lost. Objects stick together. Right? Now, of course, during the collision of two bodies, and let's animate this. Whoa, let's see. Whoa. And then let's reanimate after the rebounding. Ooh. Oh no, I grabbed some of the lines. There we go. During the collision, of course, all forces that happen, the collision forces, are all internal, and that is why the momentum is conserved. There's no external force during this collision point. So in this case, the ball and the wall are part of the system, and all collision forces that occur between the ball and the wall are all internal forces, and they all cancel each other out. Notice how there's a force on the ball by the wall and the force on the wall by the ball. These two are opposite but equal in magnitude, and the net force is 0. So the net force from internal forces, sigma F internal, is always equal to 0. Sigma fint. Alrighty then. Alright, I think that's all we're going to cover today. Thanks for tuning in. Take a look at Canvas for part C and D, see if you can figure this out, and then leave your comments below. I'll see you on Monday.